With all these work done, let's now look at a bigger example. It does not illustrate the scale challenge, which we'll come back very briefly in a moment, but it is slightly bigger than 4 nodes. Now we're talking about 8 nodes. Nodes 1, 2, 3, 4, 5, 6, 7, representing 8 web pages interconnected by directional links, these hyperlinks. If we just stare at this graph and say, which node is most important? Well, we may say by degree, in degree count, node 4 is the most important. Right? Because it's got 4, it's bigger than any of the other nodes in degrees. But if you think along the line of Google PageRank, which implicitly assumes certain navigation behavior, you see that 4 basically gives away all this importance score to a single node downstream 3. And 3 does not give it back to 4. Okay, it spreads it further to 2 and 8. So this gives you a hesitation that maybe node 3 by PageRank calculation of importance score will be higher than 4. And indeed, we see that's the case. Intuitively, 2, 3, 4 should be highly ranked, and that is what we will see. And which nodes will have the least importance score? Well, those nodes that are not pointed by many other important nodes who concentrate on them. And we can see probably node 7 and node 6 will have low importance scores. And indeed, that's the intuition will confirm in a short while. These will be lowly ranked, will be highly ranked. So to make this a little more efficient, I've written out the H matrix already, okay, just based on the topology of this given graph here. Now we can then construct H hat, but H hat is the same as H because there's no dangling nodes. And then we can construct matrix G with randomization parameter, or anti-randomization parameter being 85%. And then 15% of the time we'll be doing random hopping among the pages. Then you can write down that G matrix, and then you can start doing the iteration pi equals pi transpose equals pi transpose G from one iteration to the next. And this shows the first initialization. All the nodes have 1/8 exactly evenly distributed. It doesn't matter what initialization you use, actually. It will change the convergence speed a little, but not the end result. The first iteration is shown here. Is this vector, okay? And I'm skipping the other steps. You can see that in the textbook. Eventually, it converges to this, or something like this. Actually, this is only the 6th iteration. But it's getting quite close to the final answer. The final answer is shown here. This is the equilibrium pi vector for the 8 nodes. I have already ordered them, and I have already normalized them. So what you see here is the normalized and ordered by the importance scores in descending order. So node 3 has the highest importance score and therefore ranked in number 1, followed by node 2, followed by node 4. You can see node 3 actually is by far the most important. 0.2 sounds like a small number, but remember the pi is now normalized, so it all add up to 1. So 0.2 out of 8 nodes is actually quite impressive. 2 and 4 are about the same, and nodes 6 and 7 are by far the smallest. Okay, that's 0.06, 0.04. But then again, Google PageRank returns the ranking. It does not show you the actual scaling. So the scaling is only intermediate step. And this confirms our intuition, what we just said before, that node 3 perhaps is the most important, even though node 4 has a higher in degree. That's because PageRank calculation models the navigation behavior, saying that if a lot of people come to this web page, but then they all have to go out to this page, then this page actually shares 100% of the importance score spreading from node 4. Now, you can disagree with that navigation behavior, but given the dominance of Google search engine, it's probably hard to refute why that does not satisfy users' need, and if you can provide an even more useful ranking order. Now, there are so many more things we can talk about. We'll save them for the advanced material part, but just want to briefly mention that in Lecture 1, we looked at distributed power control for cellular wireless networks. In fact, when we generalize PageRank, the famous algorithm we just showed, a little bit, generalize a little bit, and you see what exactly I mean by that in advanced material part of the lecture, you see a striking parallel between PageRank and DPC. PageRank is used by Google for billions of searches each day, and DPC is used by all the 3G cell phones invented by a number of companies, but eventually most of them funnel through Qualcomm. And so these are two vastly different industries. This was invented in the early 90s, was in the mid to late 90s, but mathematically they have a very interesting parallel. This is a network of interfering nodes, and the topology, the graph, is represented by a matrix G, where the Gijs are the direct and interference channel gains. This is about a graph of web pages, hyperlinked and directed. Turns out there's another matrix, same symbol but very different definition, of Google matrix that help you to rank these web pages. The functionalities are vastly different, but turns out a generalized version of the PageRank we just saw has exactly the same mathematical formula as DPC. Okay. So if you're curious about that, please come to the advanced material part of the lecture. Now, PageRank can be understood from quite a few different angles. We talked about this eigenvector angle. We talked about this iterative computation angle, modeling the hopping behavior or navigation behavior of a user, or this random walk on graph behavior. There's also an economic growth model angle, which is actually what led to this equivalence. But the biggest challenge for Google using PageRank is the challenge of scale. The N is too big. But fortunately, these graphs, H is sparse, and the other graphs matrices are rank 1 matrices. So you add two rank 1 matrices to a sparse graph, you get a very well-structured graph G that helps a lot in scaling up the computation. Notice that this computation is done in a central server. DPC is done in a distributed way. That's the word, distributed power control. So there's a big contrast between those, but then again in DPC we're talking about tens of nodes. Here we're talking about millions of nodes relevant to a search, if not the entire set of web pages, 40 to 60 billion out there. There are quite a few tricks you can use to improve the scalability of this centralized computation. One is numerical linear algebra methods. Okay, there are a lot of ways to decompose this matrix H so that you speed up the computation of matrix multiplication. There are also a few more tricks. For example, it's only the order that matters, so don't worry too much about converging on the scale of the importance scores. Certain web pages can be grouped together. The dangling nodes can be treated separately, and you may also have a hierarchy. You can group certain clusters of nodes together and run an approximation before you're distributing a given importance score among those nodes in a cluster. In the homework problem, we look at this cluster-based hierarchy approximation. So whether it's speed-up method or approximation tricks, there are many approaches to make this algorithm work so fast for a large N. And finally, Google also plays a game with companies called SEO, search engine optimizations. And as soon as Google became popular around 98, SEO popped up around 99, 2000. And since then, it's been over a decade of constant struggle back and forth between the two. So SEO, in a nutshell, basically try to increase your web page's ranking by doing things that try to leverage the PageRank's algorithm. For example, they will say, here's a truly important web page I construct. Then if you pay me, I'll provide pointers to your web pages, even though your web pages may not deserve a high rank. So basically try to change this structure of the H matrix. But then Google is not sitting idle. There's also reacting. Two recent reaction is in early 2011 and May 2012, where Google announced some changes in the way they run the actual detailed version of the PageRank methods that will try to counter SEO's artificial lift of certain web pages' importance score. So there's a lot of interesting stories that we won't have time to go into. Let's quickly summarize what we have seen so far in this lecture. The key concept is that we can view the collection of hyperlinked web pages as a network. There's a graph that we represent by matrices such as H, H hat, and G. There is also a functionality of navigation that we implicitly modeling through the way we construct these matrices. You can disagree with those models, but so far Google's search result has proven to be quite useful. And this is a general theme that connectivity pattern provides a hint on the node importance. We'll come back to this in lecture 4 with 3 more additional importance metrics suitable for other purposes. So PageRank, this famous algorithm we just saw, and construct uniquely defines and then efficiently computes a consistent set of importance scores based on these ideas. And one of the angles we just saw and emphasized is the dominant eigenvector angle. That's the pi star transpose equals pi star transpose times Google matrix G.